So the weirdness about spherical is if you're doing a triple integral in the world of rectangular, and you've got some fxyz in there, and you've got your volume element. And keep in mind the volume element for rectangular, there's 6 orders of integration, but my personal favorite is dz dy dx, but there's more. That's the volume element for rectangular. When you convert this whole mess to spherical, and know that why you're doing that. I only convert to spherical when I need to, where the solid, this Q is your solid that you're integrating over, is something that lends itself well to spherical things like spheres or portions of spheres, like half a sphere is good, a quarter of a sphere, good, or things that have symmetry about the origin are good choices for spherical coordinates. Nothing else is, though. Like if somebody said, oh, my region of integration is a cube, do not convert to spherical. I mean, no. Like I don't even know how to do that. I don't even want to know. Okay, personally, don't care. So think before you start doing converting, because you only want to convert if it's making sense. Same with spherical, same with polar, the whole thing. The first example we did, they gave an entire sphere for the solid. Ah, that's awesome. Awesome. Why? Because it's easy to get your rho. Your rho is just 0 to 5. It's constant the whole way. And the trace that this sphere makes in the xy plane, remember theta is the same theta you already know and love from polar and cylindrical. And, if you look at what's going on in the xy plane, full revolution. In this sphere, remember the phi is an angle. It's like a drop down angle from the positive z-axis. It's doing the whole range of motion for phi, starting at 0 degrees, because that's on the positive z-axis, all the way down to pi being the negative z-axis. And remember, phi is restricted. It can never be negative. Theta can be negative, but phi, oh no. And phi cannot go lower than 0 or higher than pi. Ever. Like no exceptions. Theta, yeah, sure, do what you want. Phi, no. No way. So you have to be careful. So the full enchilada here, because that sphere is basically covering all the points on the sphere, covering the whole range of motion for phi. Fine. So let's keep going. We're going to do a lot more problems that I have picked out to hopefully clarify spherical. Because what I found in the past, and I'm not trying to scare you, but I'm going to be honest, spherical, challenge. Students usually get cylindrical because cylindrical is just polar with a z-axis jacked on the top. No big deal. Spherical, hard to get their minds around it. Okay, so hopefully you're paying attention. I don't know. I don't know what you're doing out there when I'm zooming. It's hard to say. I hope you're there. So we're going to do a triple integral in spherical, and we're going to find mass. So what do we know about mass? Mass looks like, if we're going to do a triple integral, you're going to integrate over the region, some solid that you're trying to find the mass of, and you're going to put some density function in the integrand, and then you'll have some volume element here. Fine. So they give you this weird solid. It's a sphere with a hollow center, kind of like chocolate covered cherries. So the outer sphere is a sphere centered at the origin of radius 3, and then they took away or cut away the center portion like that. So if you can imagine a solid with a hollow core that's also a sphere, that's kind of cool. Now they didn't give you the density function. They just said, well, the density is proportional to the distance from the origin. Oh, okay, fine. So if you took any point on your solid, say x, y, z, this distance to the origin, which is 0, 0, 0, is just going to be square root of x squared plus y squared plus z squared. And your density function is proportional to that. So it's some k times d, or k times the square root of the sum of the squares here. Fine. So mass is going to be boo, 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 triple, triple, triple. You put your density function in there, k square root of x squared plus y squared plus z squared. And, if we were doing the volume element in rectangular, then we go, okay, dz dy dx. But in spherical, dz dy dx is really gross. Like it's going to be horrible for this problem since it's got this hollow sphere. So better we not stay in the world of rectangular. I don't even want to try to figure out the limits. We probably have to cut it up into eighths and do pieces. I'm going to convert right now. So what do I know? One thing I know is that the square root of x squared plus y squared plus z squared is rho. Because if you'll recall, rho squared is x squared plus y squared plus z squared, if you go look up those conversion formulas. And then k is just some constant of proportionality, so he stays there. The volume element for spherical is rather weird. You blow this, you're going to blow the whole problem. It's hard for me to give partial credit on these. So it's going to be rho squared times sine phi d rho d phi d theta. I'm not kidding you. This is the dv portion for spherical. Well, that's really weird. I don't like it. Well, you know, a lot of things in life I don't like. Deal with it. Now what? Well, how do you get all your limits for your rho, your theta, and your phi? Well, rho is going to be going from not 0 this time. Rho is starting at the 1 and going out to the 3 because the outermost sphere has a radius of 3. Theta, if you look at the trace that this solid makes as it cuts through the xy plane, you can see you've got the full revolution there. That's what theta is doing. So it's 0 to 2 pi. And phi is once again doing a full range of motion there for phi, 0 to pi. So I'm just going to iterate this integral. Oops, 0 to, that's it. Theta is the outermost limit. Phi is the middle guy. This is just by convention. And rho is 1 to 3. And this is a pretty easy integral to integrate in triple. But before you integrate the innermost integral, which is with respect to rho, please combine your powers of rho so you get a single power rho. So then you have the integral of rho cubed. In this k, I'm just going to pull out in front. The integral of rho cubed is simply what? Rho to the 4th over 4. And you're going to evaluate that between 1 and 3. And you still have this sine phi out here. And we'll eventually integrate with respect to phi and theta. Fine. Now, this is just some constant. 3 to the 4th over 4 minus 1 to the 4th over 4. I think that's 81 fourths minus 1 4th, which is 80 fourths. Ooh, that's nice. That reduces to 20. Great. I'm just going to pull a 20 out in front of this integral. And now I'm going to integrate sine phi with respect to phi. And that's just going to give me negative cos phi going between the limits of phi, which was 0 to pi. And this is really easy, but a lot of times students do these, quote, easy problems and they just choke. I don't know, maybe they're getting too cocky. It's hard to say. Don't leave free points on the table when you get an easy problem like this, because you might. And then cosine pi is -1, but then you have a negative in front of it. Negative 1, minus is plus. Cosine 0 is 1, 1 plus 1 is 2. Pull the 2 out, so you have a multiple of 40k. And now you're just integrating 1 with respect to theta, and that's just going to be theta. Theta goes from 0 to 2 pi. Boom, 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 boom. 80 pi k is your mass. We're done with that problem. Not too hard. So what's the moral of that story? We had to work a little bit to get the density function using our knowledge of distance formula. Do you think I'm going to put a distance formula problem on the final that involves 3D? Yeah, because that's like something we learned in week 1. You don't want to forget that. Well, at least I know how to get a gradient. Okay, that's wonderful, but don't lose sight of the easy stuff too. Okay, example 28 just says set up, but don't evaluate. Just set it up. Because I just want you to be able to look at something that's already given in rectangular and then, oh dear God, figure out what it is. Like, is it even really something that lends itself to spherical region? And it turns out it is. If you look at what x is doing, x is going from -8 to +8. Y is going from negative square root of 64 minus x squared, which is the bottom half of a circle centered at the origin of radius 8. And then the upper limit, y equals positive 64 square root of 64 minus x squared. That's the upper semicircle of a circle centered at the origin of radius 8. Okay, so far so good. Now what's Z doing? Well, Z, if you go in 3D here, the Z equals negative square root of 64 minus x squared minus y squared. That is the bottom hemisphere, basically the southern hemisphere of the sphere like that. And then Z equals positive square root of 64 minus x squared minus y squared is the northern hemisphere. Okay, so what do we have here? Basically, the solid is an entire sphere. Nice. Centered at the origin of radius 8. How beautiful is that? Really beautiful, because when you convert this to spherical, your rho is just going from 0 to 8. Your theta is making the full revolution there in the xy plane, and your phi is doing the full range of motion that phi can do, which is 0 to pi. And so this integral, I'm going to kind of continue down here, boom, 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 0 to 2 pi, 0 to pi, 0 to 8. The volume element, rho squared sine phi, d rho, d phi, d theta. But then I have this nasty integrand. What the heck am I going to do there? That's terrible. If you notice, and you may not have noticed it right off the bat, that if all three of those terms have a common factor of z, and if you pull the z out, you'll get the other factor is x squared plus y squared plus z squared. So this is going to turn out to be real easy to convert to spherical. Why? Because z's conversion formula is rho cos phi, like that. And then x squared plus y squared plus z squared is just rho squared. And we're done. Now, if you did have to integrate this mess, which isn't too hard, please combine all of your powers of rho into a single power of rho, and that would be what? Rho to the 5th before integrating with respect to rho. And you can go on and do that. All right, I just wanted to point out how you look at a rectangular triple integral and figure out what the heck, what's the solid. Here's another one. It's already given to you in rectangular, convert it to spherical. Well, how do I know it's spherical? Well, let's look at what's going on here. If you look at what's going on in the XY plane, you graph everything you're supposed to, x equals 0, x equals 5, so you get some fences here, and this is the key, that you get the fences. X equals 0, x equals 5, and then here you're going to graph y equals 0. Okay, that's just this horizontal line. And then y equals positive square root of 25 minus x squared. And that turns out to be an upper semicircle, but you want the region that's bounded by all four of these fences. So what are you going to shade in? Anybody know?
In the first quadrant?
Yeah, only. Only. Be careful, only. So what does that mean? Well, let's look at what Z is doing. Z is starting at 0, and 0, folks, is just a plane. It's the flat plane here in the XY plane. That's Z equals 0. It's just a flat surface. It's a flat table. And then Z equals positive square root 25 minus x squared minus y squared. That's the northern hemisphere, like that. And so it turns out we're not going to take that whole hemisphere, because remember, in the XY plane, we determined we were only going to take the first quadrant. So that means we're going to stay as in the first octant. So if you can imagine here, only the first octant portion of the sphere, this part of the sphere where x and y and z are all positive coming out of the piece of paper, you're only getting 1/8 of a sphere here. Somebody cut it up into eighths, and we're only going to get that eighth there. Okay, so rho is going to go from 0 to 5. Theta is only going from 0 to pi halves. How come it's only going from 0 to pi halves? Because theta always does what, if you look here in the XY plane, it's just that quarter of a circle and centered at the origin in the first quadrant. So 0 to pi halves. Now what's phi doing? This is where students choke. So far, we've always had phi in my last 3 examples do the full Monty, 0 to pi. Take on the whole range from the positive z-axis all the way down to the negative z-axis, 0 to pi. But I claim that's not happening here, because we only have a portion of a sphere, not the full sphere centered at the origin. So can anybody gander a guess here?
Is it pi halves?
Yes, good. You're starting here at the positive z-axis, that's 0 degrees, and then stop. If you get to just the XY plane, that is a stopping point of pi halves, 90-degree angle. So your phi is 0 to pi halves. Fantastic. So once we start converting this triple integral here, we're ready to go. The dz dy dx is the volume element. So I'm going to go, before I forget, rho squared sine phi d rho d phi d theta, and then iterate my integrals here. I got 0 to 5. And both angles happen to be 0 to pi halves this time. Does that always happen? No, but it did here. Now, how do you convert this integrand, 1 divided by 1 plus x squared plus y squared plus z squared, into spherical? Well, x squared plus y squared plus z squared is rho squared. And so this is now converted. I'll give you partial credit for that. Congratulations. But now if you're going to integrate with respect to rho, how are you going to deal with 1 over 1 plus rho squared times rho squared? Anybody have an idea? Okay. Well, I give this to my Calc 2 students. So if you're graduates of Calc 2, you're supposed to know how to do this.
So
Not yet.
Oh, it's an identity?
No. I'll give you a hint. Say that again.
Oh, div-
Do you do long division?
Yeah, thank you. Thank you so much. Yay. Congratulations. You get the Bendix washer dryer behind door number 3. Yes. Polynomial long division. You got that right. Really? Yeah, really. So, you know, and it's not that bad. This one's easy. But you should know how to do it. Like, you know, and I know Briggs doesn't really have a lot of polynomial long division in the text, which is unfortunate because when my students get to DiffyQ, that'd be Math 253, and they can't do polynomial long division, and not on my watch. Oh boy, no. So rho squared goes plus 1 goes into rho squared how many times? Well, rho squared goes into rho squared once, okay. And then when you subtract, you get -1 as your remainder. And now you rewrite this as a quotient plus remainder over divisor type of problem. And this is arctan right here. And so this ends up being rho minus arctan rho. Oh, okay, fine. So we're done with the scratch. Go back to the problem at hand. We're going to evaluate rho minus arctan rho between the limits of 0 and 5. And arctan of 0 is 0. So this is just going to be a weird problem. It's going to be 5 minus arctan 5. And I would just, it's some constant multiple, pull it out in front of the integral and call it a day. Okay, it's just some weird wacky number. And it will be part of our final answer. Okay, now you're going to integrate with respect to phi. And you're going to integrate sine phi, and we already did this because it was minus cos. So you're going to have minus cos phi, and that's going to go from 0 to pi halves. And cosine of pi halves is 0. So then you're going to have minus cosine 0. So this is just going to end up being a 1. Oh, how convenient. So now to wrap this up, you're just going to integrate a 1 with respect to theta, and that's just going to be theta. And theta's limits were 0 to pi halves. So then your final answer is going to be this weird, wacky number, 5 minus arctan 5. I don't even want to know what arctan of 5 is. Yucky. Times pi halves. And that's your answer. Okay. Any questions on that? A lot of conversions going on, but you had a portion of a sphere, not the whole sphere. So that was the point there, and know how to identify when you have a portion of a sphere rather than the whole sphere. Don't assume it's always a whole sphere when you're converting to spherical. That's a dangerous mistake. Okay, now the hard one. This involves a cone. So if you did graph z squared equals x squared plus y squared, you would get what's called a double napped cone. It's like an ice cream cone pointed upward, and an ice cream cone pointed downward. Really? Yeah, it's kind of funky. And it turns out for this this problem, you're only going to want the upper cone, and you'll see why in a moment. So if I turn this around, you can see, ooh, double nap cone. That is beautiful. All right, nice. Okay, and then what else am I looking at here? Well, I've got x squared plus y squared plus z squared equals 9. Okay, I hope you guys can appreciate that that is a sphere of radius what?
3.
So if I graph, what I'm looking for now is the intersection of these two surfaces that's going to form the boundary of my solid. So let's just see if we can get a handle on what the heck's going on here. Whoa, what a mess. Oh, that didn't look too good. My parameters aren't good. Oh, I see why. I need to get more X and Y range here for this software. I guess it always defaults to something tiny. That's too bad. Okay, let's see if that will make it look better. Okay, now, whoa, yeah. Isn't that cool? Oh my goodness, that looks so neat. All right. So if I can change colors. Oh, that's even better. Okay. Do you see that if you take the upper napped cone and look at the little cap there, that red portion of a sphere, that's going to be the capping surface, and then the cone sides will be the side walls of your solid. What? Yeah. So if I were to graph this, we want just, oh, that didn't go well. Sorry. So you've got the upper nap cone there, and then the ice cream there, that's the portion of the sphere that's making the ice cream there. So this is our solid. It's an ice cream cone. How cool is that? Yeah, go find the volume of an ice cream cone. Nice. Yeah, well, at least we have some relevance here. Love it. This is a hard problem because it's not apparent, what some of the limits are. So you have to be a little bit careful. It's going to be a little bit weird here. Okay. So it's going to turn out that on this ice cream cone, because we're looking at this right here, that is a portion or a cutout of a sphere. So rho is going to go from 0 to 3. Okay. Now, as I mentioned before, like what was on the quiz problem, when you're doing a floor and a ceiling here, which we're doing the ceiling is the sphere, and the floor, the underside or the underbelly of the solid is the cone. So you're going to have taller minus shorter. But the outermost fattest portion of the solid, the shadow that it makes here in the XY plane is what X and Y are going to be doing. So you're going to have to figure out the intersection of these two surfaces, which gives that sort of ridge there where the ice cream meets the cone. So normally you do Z equals Z, okay? But both of these equations are given with Z squared. So it's going to be good enough if we instead just do Z squared equals Z squared, because that also has to be true. So for the sphere, if you solve for Z squared, you get 9 minus X squared minus Y squared. And for the cone, Z squared is X squared plus Y squared. And if you add X squared and Y squared to both sides and then combine like terms, you're going to get actually a circle centered at the origin with a really bizarre number for its radius. So what's the radius?
3/√2.
Okay, yeah, it's 3/√2. Yeah. So 3 is like crazy. 3/√2 is going to be, so there's what's going on in the XY plane, and that's helpful because that tells you what theta is going to be doing. Theta is going to be doing the full revolution, because that's what, if you look in the XY plane, the theta that you know and love, making an angle with the positive x-axis, 0 to 2 pi. Fine. Now the hard part's what the heck is phi doing, because we already got our rho, We already got a theta. Now what the heck about phi? Phi is the angle between the positive z-axis. So we know that some of the points of the cone do live on the z-axis. So our phi is definitely going to have a lower limit of 0. But what's the most it gets? The most it gets is whatever that angle is right there. So it, it's somewhere in between 0 and pi halves, because pi halves would be if the cone, was flattened into the xy plane. So this is the hard part, getting that angle. So the way to do it is if, and this is a little bit sort of weird, but if I start over, if I look at x squared plus y squared plus z squared equals 9, that's the sphere. And I know that from the cone, x squared plus y squared is equal to z squared, because that's what the cone tells us. If I then rewrite this sphere equation as e squared plus z squared equals 9, because I'm talking about that ridge, that intersection, right, where the cone and the sphere meet, then I can combine like terms, and you're like, oh man. So z squared equals 9 halves, fine. So z is equal to plus or minus, but we'll take the plus. And if we did the plus or minus, you'll see what's going to happen here. I'll just leave it in there. So then what? But z is equal to rho cos phi when you use the conversion formulas for spherical. So you got rho cos phi has to equal this plus or minus 3 over square root of 2. But rho, remember, if you're on the sphere, it's a 3, because our sphere equations, by the way, if you rewrote the sphere equation in spherical coordinates, the spherical equation for this would simply be rho squared equals 9, and then square root it, and you get rho equals 3. That's the equation of a sphere. It's always centered at the origin. It's always nice. So you 3 cos theta, phi rather, equals plus or minus 3 over square root of 2. Divide out by 3. So cos phi is equal to plus or minus 1 over square root of 2, but that's the same as plus or minus square root of 2 over 2. And if you take cos inverse of both sides, you'll get 2 angles, but we only want the one of them. You'll get pi fourths, and then I think you'll get what, like negative pi fourths, which you're not even allowed to get. You get like so you don't want to go there. So because arc cos, the range is from 0 to pi, so we'll stick to the posit. Now what? I hope you'd agree that this angle that this cone is sort of sketching out here for the phi does look like it would be pi fourths, like a 45-degree angle. And that's exactly right. So your volume here of the ice cream cone, when you set it up, is going to look like this. That's the generic version. Your volume element for spherical is rho squared sine phi d rho d phi theta. And we got 0 to 2 pi for theta. We got 0 to pi fourths for the phi. And we got 0 to 3 for the rho. And this is pretty easy to integrate. I'll let you integrate it. And then you get for the ice cream cone, I get 9 pi times 2 minus square root of 2 cubic units. Wow, that is wacky. That's not a very nice number. Yeah, I know, but it's positive. So there's your volume of your ice cream cone. And if you're an engineer, you should know how to find the volume of an ice cream cone. Why not? Something to brag about at the next party you go to. And that's about as hard as it would ever get in spherical. I usually try not to do weird regions like that because they take too much time, but you'll see. Okay, now let's look at a multiple choice problem. There's not much to do here, but we're trying to set up a triple integral in spherical that would find the volume of an entire sphere. Now, folks, the volume of a sphere, you don't need a triple integral. That's like overkill, because the volume of a sphere is 4/3 pi r cubed. And you would never need to use the triple integral to get it. But if you were integrating over a sphere, that was the region of integration, and you were maybe trying to find the mass of it, or you're doing some other triple integral, which when we get into vector calculus, we'll be using triple integrals to find flux of magnetic fields or electromagnetic fields through solids, which is kind of fun. So you better know this. So they won't be asking you for volumes, but they'll be integrating a triple integral over some solid. Okay, so how do you do that? Well, knowing that a full sphere of radius, in this case 10, if I just did the full sphere as is, my rho would be 0 to 10. The trace that this sphere makes in the xy plane is a circle, so the theta would be the full revolution, 0 to 2 pi. And phi is doing the full range there from the positive z-axis, which is 0 degrees, all the way down to the negative z-axis, which is pi. So I'd like to see the volume look like this if I did, and then rho squared sine phi d rho d phi d theta. Do any of the answers look like that? And it's like, no, none of these choices look like that. That sucks. So why not? Because it looks like they all have an 8 here, 8s everywhere. Oh, bummer. Well, what does that mean? It means they're using symmetry of the sphere. They cut it into 8s. And if we only talk about an 1/8 of the sphere, let's talk about the first octant region only. So if we were looking at the first octant region only of the sphere, that'd be the 1/8 of a sphere that's coming out of my paper, where x, y, and z are all positive. We'd still have rho go from 0 to 10. That's not changing. But now the 1/8 of a sphere is, if you look at the base of it in the xy plane, it's only doing the first octant. So when you limit yourself to the first quadrant, you limit yourself to the first octant in 3D, that means you're limiting yourself to the first quadrant here. So this is going to limit my theta. Theta is going to only go from 0 to pi halves now. Okay. And then what's phi going to do? Well, phi is not going to do the whole, range. It's only going to start here at the 0 degrees on the positive z-axis and then stop down here at the xy plane. So what is my range of theta now? It's not 0 to 2 pi, I'll tell you that. I mean, my phi. What's phi doing? It's not 0 to pi.
Is it pi over 2?
Yes. It's going to go from 0 to pi halves, because once you stop in the xy plane, that's the pi halves. So what we want now, instead of these limits that I had before, it looks like both theta and phi will be going to pi halves. And since we are using the symmetry, we'll multiply that guy by 8 in order to get the full volume of the sphere. Okay, so does anything look like it's going to match this one?
B.
B is correct. Okay, are there any others?
E?
E is correct. Why?
Because it's just a different quadrant.
Yeah, they're just taking the 3 pi halves to 2 pi quadrant instead, and everything else is staying the same, and that's still legit. If they were using this triple integral to find the volume of a sphere, I'll go with it. So it turns out both of those are good. My personal favorite, though, is not E, it's the B as in boy. That one is, because I usually stick to the first octant when I do stuff, if I can. Then not all solids are relegated to the first octant, so be careful. Okay, so that one is nice. And then here's a meme. Doesn't mean to scare you, uses triple integrals in first year math. Oh my gosh, okay. So this last example I stole from the internet, and then we'll do average value. And I saw this on a, I think it was a final exam for some Calc 3, I don't even remember where, some other university, 4-year university somewhere in the United States. And I just thought, wow, this is awesome. Okay, so which one of these choices, or none of these, is the correct conversion from spherical to rectangular? So this one's a little tricky because we've been going from rectangular to spherical the whole time. So what if you have to do the reverse? Yeah. So what I like to do before I try out anything is I look to see what are these limits doing. Phi is the outermost integral, which is kind of rare. I usually use my phi as the middle integral, but okay. So phi is doing the full enchilada, going from 0 degrees and down to the negative z-axis here. to pi, okay? And then theta is doing a full revolution, 0 to 2 pi, okay? And then rho is going from 0 to 2. So you know what this tells me? It tells me the solid is a sphere, an entire sphere, centered at the origin of radius 2. So here is your solid. Easy peasy. Solid sphere, centered at origin, radius of 2. Nice. That's easy peasy. Or is it when you convert to rectangular? So hopefully that you get that x squared plus y squared plus c squared equals 2 squared, which is 4, is the equation of a sphere for us if we're using rectangular. And if you're trying to do, if you let z equal 0 and just look at what's in the xy plane, set z equals 0 to see what's going on in the xy plane, then it's just going to be the graph of x squared plus y squared equals 4, like this. And so then your x is going to go from -2 to 2. And it looks like your y is going to do the bottom half of the circle. So the lower semicircle, negative square root of, 4 minus x squared. And then the upper limit for y would be the positive square root of 4 minus x squared. And then here in the z world, the lower limit for z, if you're looking at the floor of this solid, is the bottom half, the southern hemisphere. And if you solve your sphere equation for z, you'll see that you get two choices, the northern hemisphere and the positive and the southern hemisphere. So your z is going to range from the lower hemisphere all the way up to the positive, the upper hemisphere. So look at all of these choices, and it doesn't look like any of them do that. Why not? Because they're dx, dy, dz. Yeah, that's a bummer. So, but you can use this thinking if you turn sideways. Yeah, you can turn sideways. And then think about your YZ as being your flat XZ plane. So then you'd still have by symmetry, Z would go from, his limits would be -2 to 2, which it looks like these two are doing. So it's definitely not going to be C. And then y would be going from negative square root of 4 minus z squared up to positive 4 minus z squared. It looks like both of those are going. And then the x, if you solve your sphere equation for x, instead of solving it for z, you'll get plus and minus the square root of 4 minus y squared minus z squared. So it looks like A and B are tied right now. So which one is it going to be?
B.
So what's wrong with A? B is correct. That is the correct choice. What's wrong with A? Why is that wrong?
Add an extra value of B. I'm sorry, rho.
Yeah, when they convert the 2 to the rho plus 1, both of them are doing that correctly. 2 to the 1 plus square root of x squared plus y squared plus z squared. But this rho squared sine phi d rho d theta d phi, that is the volume element. And that converts directly to, dx, dy, dz. So this extra x squared plus y squared plus z squared, it looks like they were thinking the rho squared had to, which is equal to x squared plus y squared plus z squared, but that isn't put into the integral when you're going from spherical to rectangular. So letter B is the only correct choice, and that's basically testing if you know your volume element for spherical. And that's why I love that multiple choice problem so much. Really tests if students know their volume element for spherical or not. It's kind of a nerdy thing on my part. So now let's look at average value. So how do you do average value for cylindrical and spherical? Well, keep in mind that average value, if you're going to be integrating over a solid, is 1 over the volume of whatever your solid is. We'll call it Q. And then you're evaluating a triple integral over Q, and you're putting the function there in the integrand. So whether you're doing things in rectangular, cylindrical, or spherical, it's all going to be the same as long as you honor the average value formula here. So they're telling us that the solid is a cylinder with radius 1. So if I were going to draw it, so there's a cylinder, but it's between the plane z equal 1 and z equal -1. So that's the top and bottom of the can. And you know what? I could set up a triple integral to find the volume of Q, but I think a quicker way is just to use the fact that the volume of a cylinder, this is a right cylinder, is pi r squared h. So let's just use that quick and dirty formula for this cylinder. So pi r is 1, and this height, I hope you can see, is 1 minus a minus 1, which is 2. So the volume of the cylinder is 2 pi cubic units, and that's what you're going to put in this denominator. So this F average right now looks like it's, for me, it's going to be 1 over 2 pi times a triple integral. And then the, this is kind of an easy integram there, R. And then they told me that they wanted cylindrical coordinates. So what's the volume element for cylindrical? Anybody remember?
Are you talking about the rho squared sine phi?
Okay, that's for spherical, but
Oh,
we're
sorry.
doing cylindrical. What's the cylindrical volume element?
Is it R dz dr d theta?
Yes, R dz dr d theta. Thank you, Alan. Awesome. Okay. And then what are the limits? Well, shoot, man, if you look here, the cylinder is cutting through the XY plane as a circle. Yeah, and it looks like it's going to be doing the full 0 to 2 pi thing. Oh, yeah. And then R, if this is what's going on in the XY plane, it's just a circle of radius 1. So R is going from 0 to 1. And then Z is the floor is just this flat plane, -1 up to the positive flat plane, Z equals +1. Boom. And I'm pretty much done. I think you can probably integrate this, although you do want to combine your powers of R together in a single power of R. And I'll just put et cetera, et cetera. You go do it, and you'll get 2/3 is the final answer after dividing by that 2 pi. Spherical, you're going to use the same formula for finding average value, but here they're going to give you a function of f rho phi theta, and they gave it to you. It's just rho. Oh, that's nice. And you'll have a volume element over Q. Now they're telling you that the solid Q is just a solid ball, rho less than or equal to 1. That's a sphere centered at the origin of radius 1. If you graphed rho equals 1, boom, there it is, sphere. So what does that mean? Well, all your limits are going to be super easy to get. Your theta, if I go d rho, d phi, d theta, theta is going to go 0 to 2 pi. Phi is going to do the full range, 0 to pi. Rho is just 0 to 1. They gave you this F, it's just rho. And then your volume element involves rho squared and sine phi. And the volume of Q, let's just use our knowledge of volumes of spheres, 4/3 pi r cubed is the volume for a sphere. And they told us the radius is 1. So this denominator will simply be 1 over 4/3 pi. And then you can do all the rest of this and get an answer. And I get 3/4 is the final answer for the average value. And we're done. Now, one last thing, and I don't feel like doing this whole problem if you want to come to office hours and have me do it, because it's going to take me a long time. But it's on your homeworks, and I don't want people to go, I don't get it. You didn't cover it in class. If you are doing average value over a surface area, you're not going to like this. But you're going to first go 1 over whatever the surface area is of your, surface times, and then this is a double integral. You're going to do a surface integral, which I taught you how to do already. What's that? So you're going to have 1 over surface area of surface times the double integral square root of 1 plus fx squared plus fy squared dA over a region. Okay. Now this problem here, the fxyz, this is sort of the tricky part, because the cone, that's not the thing that you're going to go do the fx and the fy on. It's this guy. This is your surface. So you're really going to solve this for z, and then they're telling you z lies between 0 and 2. Great. So then you only have to worry about the positive square root. And then here's how this is your fxy. So you're going to get your zx, which is your fx. And after using the chain rule, it ends up being x over square root of x squared plus y squared. And the zy, you can call fy, is y over square root of x squared plus y squared. And these guys are the guys that you're going to like put down here in the integrand. It's going to be pretty messy. So it's, you know, you'll figure it out. It's whatever. And then this surface area, you're going to have to set up the surface area of the cone. You're going to have to set up another one of these surface integrals just to do that. Oh man, are you kidding? Yeah. Oh, by the way, sorry, this shouldn't be a 1. This is the fxyz. Sorry, my bad. And then here you'll put your fxyz in there. And the weird part, so your surface area of your cone will have a 1. You use a 1 when you're doing surface area. So I do want to say one thing, and this will help you when we get to vector calculus. You're not allowed to have z's in an integral that only has x's and y's in it. That's forbidden. So even though this is given to you as 100 minus 25z, and then you'll have that nasty square root, and then you'll do, you know, dy dx or whatever you end up doing. This z needs to get replaced by the cone. So you'll substitute this in place of the z. I only put one of those problems on in my math lab for you. I did want you to see it. Good news, I'm not going to put that on the midterm, okay? Doesn't give you permission to skip it, but I know a lot of you will. So I'm officially done with spherical coordinates. Congratulations. Okay. So that is the end of chapter 16. So I'm going to start vector calculus today, right now, just a little bit. I just want to do a little bit of vector fields for us so we could get a head start. So Friday, I was hoping to get a little bit further here, but it is what it is. At least on Friday, we'll test for conservative vector fields and we'll start some line integrals. That stuff won't be on the exam, okay? And I know I'm going real fast right now, but we're jammed for time because we're getting near the end and I got to finish. Okay. So on the exam, what can you expect? What you can expect is something similar to the quiz that you just took on Monday, or you finished by Monday. And you'll have for sure a cylindrical, spherical, and a couple, maybe even 2 spherical coordinates thrown in there also. So it's going to be similar challenge level to Monday's, but it's going to have some of this stuff I just wrapped up and some of the previous week's quiz, although the previous week's sort of was embedded in this last quiz, but there will be definitely a switch the order of integration. Like you can count on that for real. So you're going to do that at least once on your exam because that's a skill you need. Okay. So please study. I encourage you to make a formula sheet. I know some of you just go, well, I'm good. I'm not going to study that hard. I got my course reader. But then you spend all wasted time thumbing through your course reader and then you run out of time. And that's a drag. So my advice, and I know some of you ignore it, but I would suggest making a formula sheet that has all your key formulas on there, maybe your volume elements for everything, all that stuff, surface area formula, because that's wacky, all that stuff. Have it. Be ready. Okay, any questions?
No.
Okay, so let's see here. Let me go back to sharing screen. I'll show you some really fun surfaces here just to get you a little motivated. So this is a really cool surface right here. I thought that I'd share with you. See if I can move this down a little bit like that. Okay. That's a neat surface. And then what else we got here? Here's a really cool surface. Check this surface out. It's if you look at the equation for it, it's got some ends in there. Yeah, it's a surface. And oh, bummer, I just got rid of it. What happened? Okay. So The n is variable. So it's sine nx plus sine ny plus sine nz, where n is a positive number, you know, let's say between 0 and 1. So I'm going to play this as a video. Really? It's a video? Yeah, check this out, where n is going to vary. And watch how the surface changes shape when n changes to different numbers, where everything else in the equation stays the same. This is so cool. So n is changing all the way, I think, from 0 to 7. Isn't that neat?
Wait, why does it do that again?
The n, can you see the equation up here? X squared plus y squared plus z squared
Yeah.
plus sine nx plus sine ny plus sine nz equals 1. That's a representation of a surface. But the surface changes its shape based on what n is doing. And in this little video I'm playing, if you look at the bottom slide bar down at the bottom there, n, and whoever wrote this code is changing the n from, you know, something really close to 0 all the way up to, I think the highest it gets here is just 7.
Almost looks like it's absorbing.
Pretty interesting, huh? Surfaces, man, they could be fun. You should be duly impressed right now, okay? Because you're studying surfaces, folks, right now. You're looking at surfaces, finding surface areas. You know, when we do surface integrals for realsies, when we get to vector calculus module, which we're starting right now, you know, you're going to be finding, say, the flux of some field through one of those weird looking surfaces. Could be weird, could be fun. I don't know. All right. So I'm going to close this out and we're going to start the vector calculus module of this course. Okay. Oops, I just blew it. That's hilarious. Wrong one. What is a vector field, people? It's a function. It is, yeah. Well, what kind of function? Well, you know, it's a special kind of function, but I wanted to show you some graphs of vector fields first. So let me just get there. Oh, come on, baby. Yeah. Yeah. I got all kinds of goodies here. Vector fields. Yeah, that's it. All right, let's see some two-dimensional vector fields, some easy ones, because you're going to be graphing some 2D. So what the heck? Ooh, wow, that looks pretty cool, doesn't it? So you see all these little tiny vectors in this cool graph? That's a vector field. Now, if you can imagine that the arrows are representing sort of the motion of maybe a fluid, that's a good way to think about it. You could think of this as being the motion of a jacuzzi, and all the jacuzzi jets are whoosh, like over here you've got circular motion, over here circular motion, another circular motion in the center of your jacuzzi. Ooh, looks like a pretty comfortable jacuzzi. Nice. Okay, so what else? We look at another 2D vector field just for kicks and giggles. This one isn't maybe as interesting as the jacuzzi one, but you can still imagine these arrows as representing fluid motion, and you can see the dots. The tinier the arrow is, then there's less movement or less whooshing of the jacuzzi. So this is an interesting looking vector field there. Not bad, not bad. Okay, fine. Shoot, man, let's get something more fun. Let's do 3D vector fields. Yeah, baby, what is that? Oh yeah, let's go for, let's see what we got here. Oh, nice. So if you look here, it's kind of hard to see, but those are like little tiny vectors there. See that? Ooh, cool. That is a vector field, people. Nice. And so if you look at the equation for it, it kind of has the look of vectors, you know, because it's got the, these are column vectors. Which some of our linear algebra brethren use when they're doing their vector notation, but let's check out another one. Let's see another 3D vector field. What the heck, for fun. Oh, okay, this one has a little bit different look to it. Looks like it's sort of whooshing over to, like whooshing over. All the arrows are kind of pointing in a sort of a right circular motion there. That's kind of different than the one that we just saw over here. Oh, you may argue it's the same. I don't know. Have to see. Let's see if there's something else here that might be fun. Okay, this looks like another one of those videos where n is variable. So again, imagine n being a constant, and so I'm going to play this video where n is going to vary between, ooh, something negative. They're going from negative to, it looks like the highest they get is a 3. So it's changing the direction of those arrows for sure. I hope you can see, if you're really looking close, that this little video we're playing here of the arrows changing directions. Whoa, that is so awesome. Okay, vector fields. So if you can imagine, and if you're a physics person and you're really into physics, vector fields, the relevant application could be gravitational field, electric field, magnetic field, electromagnetic fields, or you could just stick to velocity of, you know, water particles in a pool or something like that. That would be a legitimate way to think about what this is representing. Okay, are you excited yet? Wind direction is fine, Nathaniel. Yeah, wind. Absolutely, I'll go for that one too. Good application. Okay, so what the heck? What are we doing with vector fields? Glad you asked. Or are you? I don't know. You know, as my dad likes to say, if you can't stand the answer, don't ask the question. Thanks, Dad. Didn't want to do it. Let's see what happened here. So let's start with what a vector field is, and then we'll do official definition, and then we'll look at some pictures, some more pictures, and then we'll look at trying to draw one, and then I'll set you free. Okay. So what is a vector field? It's a function. And so you already know some functions. So let me just remind you, I like to do these little function machines. If you just have what you studied in Calculus 1, a function of a single variable, you feed it a real number, x, and then the range are also real numbers, y. Okay, that's basic. Then one thing we did when we studied the module on vector valued functions, let me remind you, because it's coming up, it's going to be on the final. What do you feed it? You feed it a real number, t, and then the output is a vector. In this case, since I just did a two-dimensional vector field, it'd be a two-dimensional, say, constant vector like that. So that would be this guy right here. Now, before we do the vector field function machine, which I'm going to do in 2 seconds, I want to do one more function machine here, because there is another kind of function you studied in this whole course. It functions of more than one variable, because it's similar to the vector field, you'll see. So what did we feed a function of, say, in this case, 2 variables? We fed it a point, not a real number. We fed it a point, x, y, and the output was just z, the altitude, if you will, a pure real number. So that was a function of 2 variables function machine. So a vector field is a function, but it's a function where you feed it a point. In this case, it'll be an ordered pair, but you could have vector fields that have 3D. And then the notation is a little bit wacky. So it is vector notation because it's a vector field, people. You'll have a function here, I'm going to call it m, and it's a function of 2 variables, say x, y, and then comma, and then another function of 2 variables, say n. And I use m and n. Briggs uses p and q, or I don't know what Briggs uses. I don't even care, because Briggs is just wrong, wrong-o. I will not use P and Q. And if you take differential equations and you study exact equations, they use M's and N's in every single differential equation book known to mankind here up on my shelf, plus more. And so we're going to stick to convention. Briggs is sucky. Okay, the output happens to be a vector. Feed it a point, poops out a vector. Fine. So here's the official definition, the 2D and the 3D definitions. A vector field over a plane region is a function that assigns a vector to every point in the region R that's in the plane. And we saw some pictures, 2D vector field pictures. And then we saw some 3D vector field pictures too. I just showed you some graphs of those. Three-dimensional vector fields. So you have a vector field over a solid Q in space that is also going to assign a vector to a point, except the point will be an order triple and the vector will be three-dimensional. Okay. So I do want you to get this formal, and I do want you to use vector notation there. See, I'm using vector notation. You're going to have the 2D version, looks like this for all my lectures, and then the 3D version, so you have a vector field of XYZ. You'll have M, XYZ, N, XYZ, P, XYZ. Yeah, okay, fine. Briggs will use something else. It's just what he does. Okay, quick question, because you're going to just be floored when I tell you this handy fact. But you're not ready yet. And I didn't tell you 2 months ago because I kept it a secret. Yeah, I can keep secrets. So, do you remember what the gradient of fxy looks like? Sure you do. You know, del fxy looked like, you know, we would write it like this. Does everybody remember this? This is a good review for this.
Yeah, I think we had a homework question on that.
Yeah, there's your gradient. Okay, fine. So what the hell does that have to do with what we're studying right now? Like, who cares? This, folks, is a vector field. It is? Yeah, I didn't want to tell you. You weren't ready. But gradients are vector fields. They're a special case of vector fields. There's many others. But gradients have really nice properties as vector fields that we'll study eventually. Not yet, but this week, yes. So I just have on the next page some common examples of vector fields, just more pictures, basically. This, you can think of the velocity field of a rotating wheel. And notice that the length of the vectors matter. Like the longer the vector is, the more force you have. So like, for example, if this were representing a wheel spinning and you were a bug, if you were on the outer boundary of the wheel, you'd probably end up getting pushed off, you know, fly off, because it's moving faster there. Whereas if you hung out in the axle of the wheel, it's not moving at all. So you'd be safe there. And here's airflow, whooshing over the car. Gravitational fields have this look to it. It's, you know, they follow Newton's law of gravitation. Force of an attraction exerted on a particle M1 located at some other, so if M1 is somewhere over here at XYZ, there's some mass. And let's say if you have a mass over here located at the origin, it's going to give you the attraction, basically vector field between the two masses. Yeah, in physics, they do that. This is called a central force field. Here's a picture of it. Okay. Why? Well, I think you can see it's like gravitating toward the center there. Central force field. Gravitational force fields look like that. And vector fields for electric force fields also look like that. They are also considered central force fields. And notice they both have something in common. They have something squared down there, and that's distance squared. Yeah. That's very common. All right, how do you sketch a vector field? Very carefully. So I'm going to go over one example and then I'll call it, and then we'll pick this up next time. Are you going to have to graph vector fields? Yes. You have to know what a vector field looks like for real. Okay. So how do you sketch a vector field? Well, the way I do it, because I don't want to sketch 1,000 vectors. Like, do you like pain? I don't. I like to minimize the amount of work I do. So if you like shortcuts, pay attention. Anytime somebody says, hey, graph this vector field. Well, first I pull out my software that allows me to do it. But if they said, no, you got to do it by hand. And I'm like, okay. So what I do, because I don't want to have to draw 1,000 vectors on a piece of paper, is I figure out what the level curves are in the scalar field. What the heck did I just say? I'm going to show you for this example, one letter A. They want me to sketch fxy equals negative yx. We don't guess, people. You have no idea. So you're going to go, what is the magnitude of the vector field? And I want it to set equal to a constant, because that'll, whatever I get there will give me the level curve, and then I'll just pick points on that level curve and just draw the vectors corresponding to those points, not 50 million vectors for every single point on the plane. So it turns out when you take the square root of the sum of the squares of the components of this vector, and then you, oops, that should be x squared, then you set it equal to constant, and then you square both sides and, you know, clean it up. This turns out to be circles of radius c centered at the origin. Okay, fine. So what you do is you pick a value for c that's easy peasy. How about c equals 1? Oh, that's nice. So then you're just going to have a circle centered at the origin of radius 1. And I'm going to pick 4 points off of that circle, the easiest ones, the ones that live on the coordinate axes, because I'm going to make a chart. And so like this point here is the point 1, 0. And then over here, 0, 1, and then negative 1, 0, and then 0, negative 1. Those are 4 points on the circle. This corresponds to when c is equal to 1. And then the vector that's going to get pooped out is the vector that has to honor what the vector field was. Negative y, what negative y will be the first component, and then x will be the second component. Here, negative 0 is just 0. And then the x is going to be the second component. So the vector 0, 1 corresponds to the point 1, 0. Now, if you draw the vector 0, 1, do you guys remember how to draw vectors in standard position? You find the point 0, 1, and then you draw a vector coming out of the origin, because that's standard position. And there is the vector 0, 1, but you don't leave it there. You see, you need to lift this vector up and translate it so that it's sticking out of the point that it's associated with, which was the 1, 0. So now we're done with this row. And you'll do the same thing for the next point on this circle. The circle has this point here, 0, 1. What is the vector that corresponds to that point? Well, negative y, negative 1, comma, x, 0. And if I graph the vector negative 1, 0, I find the point negative 1, 0, which is right over here, and then I draw an arrow to it, and then lift it up and move it over here. So that arrow, negative 1, 0, is coming out of the point it's associated with. And I'm going to do this for the other guys here. This vector, negative y, negative 0, x, 0, negative 1. Well, 0, negative 1 is this vector that's pointing down here. So I'm going to move it over here so it's coming out of the point it's associated with. And then finally, the last point, 0, negative 1, I got negative, negative 1, which is 1, 0, and 1, 0 is a horizontal vector pointing to the right of magnitude 1. You're not done. This is not enough vectors. I won't give you full credit for this graph. Why not? Because I don't have the flavor, enough vectors to get the flavor. Well, how many do you need? 50? No, no, no. You'd be surprised. Minimal now that we're doing this level curves and scalar fields. So I'm just going to pick one more value of c, one more level curve. Say, let's let c equal 2. And that's in this equation here. And that's just going to be this circle here. And then just pick the points on this circle and plug them into our chart and see what the arrows are that correspond to those points. So that's all. And so I'm gonna do this really quick here. I'm gonna do these 4 points on my circle. Oops. And each of those points has a vector that goes with it. 0, 2. This will have negative 2, 0. This one's 0, -2, and this one's 2, 0. And then for each of those points, you graph each of those vectors first in standard position so you can see how big they are and which direction they're pointing, and then lift them up and have them come out of the point they go with. So these particular vectors are larger, bigger magnitudes than the circle that was we did first. So this is enough vectors to give me the flavor. And I'm done with this curve. So what I mean is, it looks like the vector's magnitudes get larger and larger as I get further and further away from the origin. That's kind of the flavor I wanted to see there. And it looks like a rotating wheel, the way these vectors are pointing, and that they're tangent to the level curves in the scalar field. So that's kind of cool. And we're done graphing that vector field for now. Okay. Woo! Yeah.